Estamos esto no, y la audiencia creció dramatically. The audience increased dramatically. Now there are 72 participants. So now we are going to start with a nice speaker, a nice presentation. But Luis Aguilar is the person who is going to introduce Anthony Brown. Go ahead, Luis.
Hola, hi everyone. Because people may only speak English, I'm going to switch to English. Maybe you don't know it, but Anthony is really Latin American because he was born in Aruba, in the part of the Caribbean where hurricanes do not get. He got his PhD at the University of Leiden in the Netherlands in 1996 with a study of OB associations. But then he started working on astrometry very early on using Hipparcos data. He was with us in Ensenada in Baja California between 1997 and 1999 as a postdoc. And in 2005, together with Hector Velázquez, we published one of the very first Gaia mock catalogs at the time. After Ensenada, he went to the ISO in Garching. And finally, in 2001, he went back to Leiden, where he's now a professor. And his association with Gaia comes from 1997. He was member of the working group on photometry, and he contributed to the optimization of the filter systems, or the filters using the photometric system in Gaia. And he has been a member of the scientific team of Gaia since 2006. In 2012, he was named head of DPAC, the Data Processing and Analysis Consortium of Gaia, and he heads this consortium up to now. Let me tell you that in 2018, Nature included him in his top 10 list of people with largest impact in science for that year. And I'm sure that Anthony has had a very busy day because of the publication of the EDR3 database today. In fact, I know that he was just having dinner before starting this teleconference. And for me, it is a great honor to give the welcome to Anthony and to be with us to give us this talk about EDR3. Welcome, Anthony.
Luis, it's good to be back, at least virtually in Mexico, and I hope I will make it to Ensenada at some point again in the future. It's been a really great part of my life there. Had a very nice time with good memories. But today we'll discuss the third, or the early part of the third data release of Gaia. And I speak here really on behalf of the entire Gaia collaboration, so everyone who has contributed to putting this release together. And I'll talk mostly about the contents of the release in this talk to show you the scientific performances you can get, and also a little bit of guidance on how to use the data, what to watch out for. And I will briefly touch upon the 4 science demonstration papers that we published along with the data release today. Now, just to go back in time a little bit, this is the sky map that was produced for Gaia DR1. So these are star counts, the colors being proportional to density. And of course, as you all very well remember, probably this map was full of features that have to do with the scanning law and how we filtered on the quality of the data. And then when we passed to DR2, of course, the situation improved dramatically. Most of the holes in the sky were basically filled up, much smoother map. And now when we go to the map for Gaia EDR3, the situation is pretty much the same. But if you look at the details, you will notice that there are some changes with the coverage of the sky having improved, and you will see a bit more of the banding of the scanning law. And I certainly encourage you to do this on your own machine, because it probably doesn't come across quite as well on through a Zoom telecom. About 100 million stars more in this release, so 1.8 billion in total compared to the 1.7 billion from DR2. and we'll probably keep increasing the number a little bit as we go into future data releases. Okay, so let's get into the details of the contents. So this is a magnitude histogram of the various components of Gaia EDR3. The light blue is the G magnitude distribution for the EDR3 sources, with in the background the comparison in dark with DR2. And you can notice that at the bright end we are still rather incomplete because of the saturation of the images over there, making it difficult to calibrate things. But at the faint end, we are definitely more complete. So you can notice around magnitude 19 to 20, 21 that we are above what was achieved for DR2. Now, along with Gaia EDR3, we are publishing also the same radio velocities that we had in DR2. So these are not new; they were already present in DR2, but we provide them as a convenience. The new radio velocities will come with the Gaia EDR3 in with DR3 in 2022. And then here you see 3 histograms of another important component of this catalog, which is the quasars, which we use to define the astrometric reference frame. And it plays an important role, this part, in the last bit that I will talk about when I mention the acceleration of the solar system and how we measure that with the quasars in Gaia EDR3. So I put up here the numbers. You can find those in the papers. I'm not going to go through this in detail, but as I mentioned, a total of 1.8 billion sources in the current catalog, of which about 80% has astrometry, so 5-parameter astrometry, proper motions and parallaxes, as well as colors in the photometry. And these slides will be made available through the Gaia web pages. If you go to the EDR3 release events, you will find links to the slides, so you can look back at them again. Okay, another important aspect to keep in mind when using the Gaia EDR3 data is that now we have 3 categories of astrometric solutions for the sources. So from DR2, you're probably already familiar with the fact that there is sources for which we don't have parallaxes and proper motions. They have so-called 2-parameter solution. Typically, these are very faint sources for which the observations are not good enough to make a full astrometric solution. And then there is the 5-parameter astrometry for the rest of the sources, which is the blue histogram here, where you have the standard parameters, positions, parallaxes, proper motions. Now, in addition, in this release, we also have so-called 6-parameter solutions. That's the yellowish histogram, and these histograms here show fractions per magnitude bin. And the 6-parameter astrometry that applies to sources for which in the fitting of the image profiles with a PSF, we did not have a good color for that source. So we chose a default version of the PSF, which means that you introduce slight systematic shifts in the image location. But you can still calibrate that out in the astrometric solution itself. So what we do for these sources is we estimate not only the astrometric parameters, but also a rough color for the source. And that's the sort of the 6th parameter of pseudocolor. And that's why we talk about 6-parameter astrometry. And the main difference between the two is that the quality of the 6-parameter astrometry in general is a bit less than that of the 5-parameter astrometry sources. Okay, so here we see the performance in terms of parallax precision on the vertical axis in micro-arc seconds on a logarithmic scale as a function of the G-band magnitude compared to Gaia DR1 and DR2. And the green line is the performance that we achieve now for Gaia EDR3. And in general, the parallax is improved by about 30%, but this improvement is even larger at the bright end, thanks to the suppression of systematic errors. And what you also see in this diagram are the predictions for the performance for DR4, the yellow, and DR5, the red. So DR4 will be based on 5.5 years of data, and DR5 hopefully will be based on 10 years of data. And these performance predictions are now extrapolated from EDR3. And you will also find the new performance predictions on our web pages if you're interested in simulating what you can expect in the future. Now, if we turn to the proper motion performance, and we have this diagram, this is the proper motion in right ascension. And in the case of proper motions, the improvement in performance is much better. It's about a factor of 2 or a bit more. And that's thanks to the fact that we have a larger baseline of time over which we collected observations. So 34 months instead of the 22 months for DR2. And what is interesting to note, if you compare to DR1, this blob over here, just below the main distribution for Gaia DR1, are sources for which we already had Hipparcos astrometry. And for those sources, we already had microarcsecond level proper motions in Gaia DR1. But that was because we could profit from a 25-year baseline between Hipparcos and Gaia. And now we see that at the bright end, with just the 3 years of observations with Gaia alone, we're already achieving what was done before over a 25-year time baseline. So that's another illustration of how much improvement we've achieved in the astrometry. And the next slide shows the performance in declination, the proper motion declination, which is pretty much the same picture as for the right ascension. And of course, here the predictions into the future show again much larger improvements compared to what you saw with the parallaxes, because every time you increase the time baseline, the proper motion precision goes up by a factor of power 1.5 of time. Okay, the other important aspect in the improvements is that we've suppressed the systematic errors in the astrometry. So you see here two columns with 3 plots of the quasar parallaxes and proper motions, which of course should be 0 because these are effectively at infinite distance. So any deviation from a sort of greenish color means that we have systematic errors in that part of the sky. So on the left, you see EDR3, and on the right, you see DR2, and the color scales are the same. They cover the same range. And you can clearly see the big improvement in the systematics, both in the parallaxes, but in particular in the proper motions, where the systematics have been suppressed by a factor of about 2.5. The global parallax 0 point is also a bit better. It's now -17 microarcseconds as measured from the quasars, was about -30 for DR2. And of course, in future releases, we hope to bring this even closer to 0. Also, the angular variations of the systematics, so the source-to-source correlations, have been decreased, which is evident in these maps. 26 microarcseconds RMS for the parallaxes, and about 33 microarcseconds per year RMS for the proper motions. And you can find many more details on these things in our data processing papers that also came out today in the ANA special edition, and tomorrow they will also all appear on Archive. Okay, now we turn to the photometry. So you see here the photometry performance in the 3 broad bands, so the white light band G, as well as the blue and the red broadband that comes from our prism photometers. And in particular, in the G band, you can see a very clear improvement going from DR2, and DR1, which are the light green lines, down to EDR3, the dark green line. A big improvement again at the bright end, where thanks in part to much better PSF models, we achieve much better estimates of the flux. And also the overall calibration is better. You can see that the jumps that were present around magnitude 16 and 13 have basically been removed in our current internal calibrations. The improvement for the BP and RP is also very good at the bright end. At the faint end, it's not so dramatic because they were already pretty good for Gaia DR2. And the scale, I should note here, -3 means a milliarc second. So at the bright end, you really have very exquisite photometry. Now, one important thing to keep in mind with respect to the photometry is that the passbands for Gaia EDR3 have slightly changed with respect to the ones in DR2. And this reflects the fact that we have a somewhat different average instrument that we have to deal with when we look at 34 instead of 22 months of data. Those first 22 months of data, we have a much larger fraction where we suffered from the contamination effects in the beginning of the mission. So the 34 months of data on average is cleaner, but that also means that the average behavior of the instrument is different, and therefore you get different passbands. What also plays a role is the improved PSF calibrations for the G band. And you can expect that also in the future for DR4 and DR5, our passbands will continue to evolve a little bit, simply because we on average deal with a different instrument. So keep this in mind when you use the new photometry, is that you should not make direct comparisons to the old photometry. It's really an independent system. And obviously, of course, if you make predictions about our photometry, you should really use these new passbands. So the yellowish is the BP, red is RP, and then the blue is the G band passband. Okay, here's one slide on the radial velocity. So as I mentioned, the new radial velocities will only come out in the first half of 22 when we put out the full Gaia DR3. And we expect to publish around that time about 30 million radial velocities out to magnitude 14 in RVS. But currently we still have the same radial velocities that we had for DR2. Now we did take the chance in copying them over from DR2 to EDR3 to clean up the list of radial velocities a bit. There were some spurious values, especially in the tails of the velocity distribution, which is illustrated in these two histograms. And those were essentially removed from the release. So if you are interested in something like hypervelocity stars, you have to really redo some of the studies to check that your particular sources have not been affected by these spurious radial velocities that were there in DR2. And I should note that the list that was published by Douglas Boebert, in which he had about 70,000 stars with suspicious radial velocities, we confirmed that well over 90% of them actually are reliable, and so they still appear in the new data release. Okay, now just some words on notable changes from the DR2 to Gaia EDR3. So one of the major improvements that we made is in the algorithm that takes the individual observations that we make and groups them together into what we think are sources on the sky. So the reason why we need to do this is that Gaia continuously scans the sky along great circles. And the only information we get down is the moment a source was observed, the image of the source, and the orientation of the spacecraft at that point. So from these three things, we can figure out where the source is roughly on the sky, but then, or that observation where it was taken on the sky. And of course, these observations are taken at different times, and you have to group them together in order to identify all the observations belonging to a particular source. And this matching of observations to sources has very much improved, in particular in dense regions. And here you see on the top left, sorry, an example of a dense region where at the moment we are in the input stage of this algorithm, where you have potential links between observations and known sources. And you see the same here for a high proper motion star. So you see this string of observations, and by eye you would probably fairly easily pick this out as, hey, this is just a fast moving source. But it's easily missed if you make a naive algorithm that clusters these observations together. So this was a problem in the first two data releases, and that has now been improved. So if we look at the resolution in these two cases of this linking problem, then we see that the high proper motion star is very nicely recognized as such. So all the observations along this line are grouped together with the same source. And also in the dense region, we get a nice resolution of correctly linking the observations that were done to the source that was actually observed. So this means that there are still some changes in the source list when you go from DR2 to EDR3, but it's much more stable now than when we went from DR1 to DR2. So the changes are overall at a few % level. But at the bright end, there still are significant changes where sources actually change identifier, for example, and also around magnitude 11, you have significant at the 10% level changes in the source list. So if you want to trace a particular source, your favorite source from DR2 to EDR3, you should use this DR2 neighborhood table in the archive, which tells you this particular DR2 source is matched to that EDR3 source. And it can be more than one match. Usually it's just one. And in most cases, there's no change in source identifier, but there can be changes, so you have to be a little bit careful with that. Now, a couple of other things that changed. So the reference epoch for Gaia EDR3 is now 2016 instead of 2015.5, so it's half a year later. I already mentioned, of course, the changes in the photometric system. So also the 0 points changed, not just the passbands. And the completeness in crowded regions has improved quite a bit. So centers of globular clusters, as well as the bulge region, we are now quite a bit more complete than we were in DR2, but it's still not perfect. And another important thing is that in DR2, we had a lower limit on the source separations of about 0.4 arc seconds. And below that, we considered that, that two sources so close together were actually a duplicate of each other. And one of them was removed from the catalog and the other was marked as a duplicate. And that limit has now been lowered to 0.18 arc seconds. So also the spatial resolution of the catalog has improved slightly. Okay, then we turn to the limitations in the data. I don't go through everything, just a couple of the most important ones. I refer you to our papers and the documentation for more details on this. And so here we have an example of the a plot of proper motion versus parallax, and this is for DR2. And what you notice is that there are clearly spurious parallaxes, so very large negative values, and where actually the errors are small, so they are formally very significant. And these are basically wrong astrometric solutions. Typically what happened is that there were two sources close together on the sky, and we got confused in assigning observations to the correct source. And that can really mess up your parallax, but also the proper motion. And you see the same thing on the positive side, is that there are sources that are in the same sort of branch. And these are sources where the parallaxes are simply way too large. So again, an erroneous solution. And in principle, this black line here, which delimits 550 kilometers per second, sources shouldn't really be beyond here, except for one or two extreme cases. Now, if you go to the EDR3 plot for this same diagram, then you see it's much healthier. So most of the sources are now in the allowed area, and we don't have these branches of spurious parallaxes anymore. There are still negative parallaxes, that will always be the case. And there clearly also are still spurious values, but it's much less than for Gaia DR2. And also the spurious values that are there are much less in error than they were for DR2. Now, there are several data quality indicators that you can use to clean up the data and extract the most reliable astrometry. So first, when it comes to the source list evolution, we kept track of, for each source, of how many of the observations that were matched to that source were retained in EDR3, together with the new observations, or whether lots of transits had been removed and new ones added, etc., which could be an indication that the source has really changed character, just from the way we match observations to sources. And you can use these three fields to get a feel for that, if it's of interest for a particular source to know what happened to it when, let's say, you expect a certain type of source that becomes something completely different. It might be because of this change in the source list. The other quality indicators down here are relevant for the astrometry. So this renormalized unit weight error that we published after Gaia DR2 is now part of the catalog. So you can just query on that. And then there are these four indicators here, which have to do with the characteristics of the individual images that were analyzed for the stars. And in particular, they tell you something about whether an image was potentially double or not, or maybe slightly extended. And so these are, of course, good for cleaning out the data and making sure you have the most reliable astrometry. But they're also interesting if you, for example, want to look for binary stars, even though we haven't yet published binary star solutions. Here we look at the systematic errors on the parallaxes, and you see here an example from DR2 in the Large Magellanic Cloud region, where you clearly see this pattern in the sky, which is due to systematics in the parallaxes. And if we go to DR3, EDR3, you see that this is much suppressed with the same color scale. So this is what I mentioned before. Now on the right, you see a diagram that shows the difference between the known distances to open clusters and what we measure from the Gaia EDR3 parallax. And you see that the differences are not equally scattered around zero, but there are clear systematics, in this case, as a function of magnitude. And this is even clearer when you scale by the uncertainties. And one of the things we provide is a tentative recipe to correct for these parallax 0 points offset. You can make corrections as a function of source color magnitude and ecliptic latitude. And if you apply these corrections, then you see that things get much better in the case of these open clusters. And you can find the source code to make these corrections in this GitHub repository, and there will be a paper extensively describing this. And I should stress that really is a tentative recipe, so it doesn't necessarily apply to all samples that you can think of. But the paper does give you some pointers as to how to go about making these corrections for your particular sample. But in principle, the recipe is there for you to apply. And keep in mind, of course, that proper motions also show systematics, but these are a bit more difficult to characterize than for the parallaxes. One more note on the astrometry. I mentioned before the 6-parameter solutions, meaning that we estimate along with the astrometry also a color of the star, which we name a pseudocolor. And that means that you will get a 6x6 covariance matrix when you're using this data. So you have to keep that in mind when you are analyzing the uncertainties. And what is interesting about this as well, and this is documented in the papers, is that in principle, the correlation between the pseudocolor and the other astrometric parameters allows you to improve the astrometric solution if you have independent, better color information for your source. This could be just simply the color measured by Gaia. We have good colors for most sources in EDR3, but it could also be colors coming from some independent survey. And if you plug that in, you can actually improve the astrometric estimates themselves. And it's in the appendix of the astrometry paper, you will find a detailed description of how you can do this. Okay, then we look at the limitations in the photometry. So on the left, you see an HR diagram, a color magnitude diagram of stars near the sun within about 100 parsecs, G versus the BP minus G color. And you will notice that towards the red end, at the low mass end of the main sequence, the things start to turn blue. This is not physical. This is simply an indication that we are overestimating the BP fluxes, probably due to some issue in the way we subtract the background in the images. So the recommendation is that instead you should use the G minus G RP color, and that because the RP flux is much more robust against this problem. And then you can study still without any problems the lower end of the main sequence. On the right, you see another important thing to keep in mind is that for the sources where we have 6-parameter astrometry, so the ones where we had to estimate the color as part of the astrometric solution, they turn out to be on a slightly different internal photometric system. And that's indicated here by this gray band. Those are the sources with 6 parameters in the astrometry. And then the colored distribution are the normal 5-parameter sources. So what happened there is that the sources for which we didn't have a good color at the stage of PSF fitting, they got a default PSF, and that was taken into account in the astrometry, but not in the photometric reduction. So that's why you get them on a slightly different system. But it's actually fairly straightforward to correct for them. And if you apply that correction, the two sequences nicely coincide, and you can intercompare the photometry without issue. Now, unfortunately, we discovered this too late to correct it in the archive, but we have published correction formulae, and you can find Python recipes along with our papers, or you can also do it on the fly in an ADQL query, and that's also described in the papers how you can do this. So keep this in mind when you use the photometry, and you really want to make sure that it's the most accurate possible, then you should apply this correction. Now, final word on the photometry. Many of you have been using the Flux access factor in order to clean out data from problematic photometry or even problematic astrometry. And this is something that you have to be a bit more careful with for Gaia EDR3. So first off, the recommendation is to use a corrected form of the access factor. And what we did there is we already take out the average behavior of the flux access as a function of the spectral type of the star. And that means that this corrected access factor has a flat behavior as a function of color. And in this diagram, you see the access factor as a function of color. And then the distribution is color coded by the probability that a source is blended. That's another one of the indicators that we have now in the catalog. And you can see that indeed sources that have a high probability to be blended tend to have a higher flux access, so indicative of potentially problematic photometry. On the other hand, if you look at the right-hand side, you see sources where there is no problem with the photometry, but it's simply the specific SEDs that cause the differences in the access factors. You have galaxies, quasars, RR Lyrae, and a couple of other variable types, planetary nebulae. So this flux access factor now also contains really astrophysical information and not just something about the data quality. So when you use it to filter on the quality of the data, be careful because you might be filtering out interesting things in your sample. Okay, so then a few words on the Gaia archive itself. I hope everyone has already had a chance to play with it today. So the main table, of course, Gaia source. I stress again that if you want to trace sources from DR2 to EDR3, you should really use this DR2 neighborhood table. And in the documentation, there are some pointers as to actually how to use that in combination with cross matches to other surveys that are also included in the archive. We've also included now simulations. So these are the Gaia Universe Model Snapshot and GOG, both in version 20. So you can use this directly from the archive now. And if you're interested in things like survey completeness or understanding how often or when your source was observed, there is now also a table containing the commanded scan law, so the commanded pointing of the spacecraft. This is not exactly the same as the actual attitude that we get from the astrometric solution, but it's pretty close, and for most applications, the difference doesn't really matter. And then I already mentioned the cross matches, but there are pre-computed cross matches in the archive. Unfortunately, some of them are not yet available. In particular, 2MASS is not there yet, but we hope to put that in place over the coming weeks so that you can start making use of that. And then finally here, there are, of course, with EDR3, we will discover issues like we did for DR2, and we already have one listed on the known issues page, which is namely that for about 5 million sources out of the 1.8 billion, there are no G-band fluxes for technical reasons. And we had to do an ad hoc calibration for those. And you can find the photometry in a separate file on these known issues pages. So for most applications, this will not matter. But if you happen to find a particular source you're interested in that doesn't have the G-band photometry, you can retrieve it from this particular file. And then finally, here is a list of the papers that we published. So there's a link to the Gaia EDR3 overview pages where you will find lots of information, also lots of public outreach material that we produced. These are the papers that deal with the data processing itself and the summary of the archive contents. So this parallax bias versus magnitude, color, and position, that's the one that describes the 0-point corrections. There will be a paper that describes how the radio velocities were cleaned. The catalog validation is a good paper to look at. It gives more guidance again on how to use the data and what the quality is. And I point you in particular to the paper that describes how we made the source list, so how we linked observations to sources, and also how we modeled and calibrated the Gaia point spread and line spread function. So if you're really interested in understanding more about the details of your data, then these are also good papers to look at. And then finally, there are the 4 performance verification papers, so science demonstration papers, and I will turn to those next, just briefly summarize each of them. And I encourage you, I mean, obviously I don't have the time to go into the details for all these papers now, but I definitely encourage you to invite the lead authors of those papers or their colleagues to come and talk about their results. Okay, so the first of the performance verification papers is about the inventory of stars near the sun. So this is the Gaia catalog of nearby stars. And this is a very carefully constructed catalog of about 300,000 stars within 100 parsecs from the sun. Now you can of course ask what's the big deal? You just select stars with parallax larger than 10 milliarc seconds and you're done. Well, of course, the parallaxes carry errors on them. And if you want to actually have things within 100 parsecs rather than within 10 milliarc seconds, you need to be a bit careful in inverting parallaxes into distances. This was very carefully done here with the Bayesian estimates of distances, etc. And they also made sure that the astrometry of these sources is very clean. So it's really a very accurate inventory of the nearest 100 parsecs around the sun. And this infographic basically shows that within the 100 parsecs, obviously Gaia is the biggest contributor to our inventory. Hipparchus did a little bit, as well as ground-based observations. And of course, if you go closer to the sun within 10 parsecs, then Gaia doesn't contribute so much. Much of that was already known. So if we look a bit more at the scientific details, so in this HR diagram over here, you can see the distribution of the blue points. These are stars that are part of this Gaia catalog of nearby stars. And the yellow points are also objects that occur in the Gaia catalog, which are formally within the 100 parsecs, but clearly have either problematic photometry or astrometry. And one of the things the authors of this paper did was to do, for example, work with machine learning to understand from the data which of these sources are reliable and can really be assigned to be within this 100 parsec volume. And this is estimated to be about 90% complete down to spectral type M9 for these stars. Now they make a couple of science applications in the paper, just briefly demonstrating the quality. One of them is looking at the HR diagram at the low mass end. So this is again around the M dwarfs. And you can see here immediately this well-known now Jiao gap, which was discovered just after DR2. And there is many more fine structures, in fact, that you can see on this HR diagram, something that, of course, lots of people will undoubtedly start investigating to understand where these come from. It will teach us a lot, obviously, about the physics of the stars. And the bottom two plots show the example of the Hyades cluster, which is also in this 100 parsec volume, and how it can be traced out to very large distances on the sky. So you can really see the tidal tails of this cluster. And here you see it in an XY projection on the galactic plane, along with lines that indicate a particular n-body model that happens to fit this distribution well. Okay, then the next topic is about the large and small Magellanic Clouds. So these two galaxies have been a very popular topic of discussion already with Gaia DR1 and DR2, because Gaia, of course, is very good at creating clean samples of LMC and SMC stars, because you can get rid of the galactic foreground by using proper motions, parallaxes, etc. Now, what they've done here, and what you see in this image, is that they took the HR diagram of these two galaxies and divided it up into different stellar populations, different age categories. And the color coding indicates these different stellar populations, where the blue indicates very young stars and the red older populations. And there's a pretty fine-grained division into populations that they made. And what you see very nicely in this particular image is this bridge of young stars that is crossing from the SMC to the LMC. And we can really see the proper motions in our measurements lining up along this bridge. And of course, this was already found in Gaia DR1, but now it's really very obvious in this rendering using these different stellar populations. Now, I think one of the really nice things of this study is that this provides essentially the first big kinematic map based just on proper motions for these for two external galaxies, and also as a function of stellar age. So you can see here rotation curves. So the rotational velocity around the galaxy as a function of radius, as well as the radial velocity. And it's divided up into these various populations, our Lyrae, AGB stars, young stars, etc. So you really have like sort of an integral field unit map of the LMC and SMC, but now based on proper motions, and again, for the different stellar populations. They also in this paper map the outskirts of the clouds, where you can see lots of faint features that are, of course, interesting to study. And here you see again this bridge between the two clouds, where the proper motions are clearly indicating stars moving from the SMC down to the LMC. All right, then we go to the next topic, which is about the anticenter region. The big improvement in the astrometry, of course, is the proper motions, where we have a factor of 2 better precision. And this is a good chance then to study the anticenter, where, as you know, the stars, the motions of the stars are basically mapped by just looking at their proper motions and distances. You don't really need the radial velocity in the anticenter direction. And this was done in this work. And here, again, they divided up the sample into various stellar populations. And here you see on the top left, the rotation curve for young stars all the way down to older populations, and also for the red clump, which of course you can trace out to much larger distances. And you see the same here for the vertical motion as a function of the radial distance from the galactic center. The plot at the bottom here shows the vertical motion of the stars as a function of their azimuthal motion, so the rotational motion around the Milky Way. The top row is for stars that are above the Milky Way plane, and the bottom row is for stars that are located below the Milky Way plane. And the interesting feature here is that if you look at this bin around 12 kiloparsecs or so, you see a clear bimodality, where stars above the galactic plane appear to be moving mainly downwards and at a bit slower rotational velocities, whereas you have the opposite for stars below the galactic plane that appear to be moving upwards at somewhat higher rotational velocities. Exactly what this means is not entirely clear yet, but it certainly might have to do with the disturbance of the galactic disk by, for example, the encounter with the Sagittarius galaxy. Now, the other thing you can study in the anti-center direction is the old stellar population, and is essentially what used to be associated with the halo. And you see here an HR diagram for stars with high tangential motions. And what was already discovered, of course, with DR2 is this well-known split on the main sequence between a blue and a red sequence, where the blue sequence is the remnant of this Gaia Enceladus galaxy that merged with the Milky Way about 10 billion years ago. And the red sequence is a sign of the heated protogalactic disk. And if you trace these two sequences now, again in vertical versus rotational motion, then you see that the blue sequence, so the Gaia Enceladus remnants, which are here at the retrograde velocities, you see that you can trace these out to at least 17 kiloparsecs, whereas the red sequence is more or less truncated at 14 kiloparsecs. So this is taken as a sign that indeed the protogalactic disk was a lot smaller than the current Milky Way disk. So really directly showing this, what of course was already known, that or suspected, that the disk is growing from the, or was growing from the inside out. Okay, and then we get to the final result, which I personally think is really the highlight of this release, and that is the measurement of the acceleration of the solar system center of mass as it moves through space. So how does this work? What you see here in this plot, in this image, is an apparent proper motion field of quasars. Now, obviously, quasars shouldn't show any proper motions because they're too far away, even for Gaia to measure them. So what is happening here? Now, you're all familiar with the concept of stellar aberration. So as the Earth moves around the sun, the position of stars on the sky is actually distorted towards the direction of motion of the Earth by about 20 arc seconds. So it's actually a very large effect. And we notice this effect because we are going around the sun. So we're constantly changing the direction of motion, which also changes the direction in which the stars are displaced on the sky. And that's how it also was discovered when people first started looking for the effect of parallax. Now, this particular effect of the motion of the Earth around the sun, or the motion of Gaia around the sun, we can take that out because we know very precisely what the orbit of Gaia and its velocity are, so we can correct for that. But there is another effect which has to do with the motion of the sun through the galaxy. And if you think about aberration, if you're moving in a straight line without changing velocity, you wouldn't see the aberration effect itself because it's just a static distortion of the sky. But if you change velocity, so if you start accelerating, the stars will converge more and more towards the direction of motion. And this will result, as you are accelerating, in an apparent proper motion of the stars. And so what we're doing here is we're making use of the quasars, which normally should not move, but they do show an apparent proper motion pattern. And this is entirely due to the fact that the sun is being accelerated as it moves, or the solar system barycenter is being accelerated as it moves through space. And you can see that these proper motions are converging in the direction towards the galactic center. And this is, of course, what you expect, because the dominant force acting on the sun is essentially of the main mass of the Milky Way as it orbits around the center. So what we did in this release is take the 1.6 million quasars in Gaia EDR3. So you see here the distribution on the sky. And they did a vector spherical harmonic analysis of the proper motion field of those quasars, which should be zero. But of course, thanks to this aberration effect, there is a slight apparent proper motion. And this systematic pattern is again shown over here on this globe. And when you make the measurement, it results in a proper motion pattern with an amplitude of 5 microarcseconds per year. So that's extremely small. And that corresponds to an acceleration of 0.2 nanometers per second squared. And it's measured with a precision of 16 picometers per second squared. So that's really an absolutely amazing measurement of being able to measure such an incredibly small number. And it's the first time that we did this in optical astrometry. And you see over here the error distribution of the direction on the acceleration on the sun. And you can see that it doesn't peak exactly at where we normally define the galactic center to be, but it's slightly to the right and below of the galactic center. And this has to do with the details of the mass distribution in the Milky Way. And of course, there is a lot of information in that sense in this acceleration about the mass distribution around the sun. And I should stress again that this acceleration measurement is an absolute measurement because it's done with respect to the distant universe. Okay, that was it for the slides. So I'll stop here and I'm happy to take questions.
Okay, thank you, Anthony, for an awesome presentation and awesome plot. At the beginning, we were worried because the audience was very reduced, but now we are 10 people. Thank you, everyone. Questions, comments, please. Okay, Carlos, go ahead.
Good morning, Anthony. Very beautiful talk, and this is super exciting. I wasn't expecting when I woke up in the morning to be at 3 hours later. So excited. This is amazing.
Great. Good to hear.
I have one question. I read, that's too much information, but at some point it says that you're going to be releasing Bayesian estimates of UVW directly.
No, we don't have any plans, and no, not ourselves. There are plans now again to make a Bayesian distance estimates catalog. That's work being done in Heidelberg, and that will come out maybe next week or something. So they're working on that now because they had to wait for the data to be public. Okay. But we don't have plans for kinematic estimates.
Okay, great. Because I was going to ask if those were affected by all these systematics, but then it must be some separated catalog.
If you start looking really into the details, yes, they will be also affected by the systematics. So that's something that you need to, at least in a statistical sense, take into account. Yeah. Mm-hmm.
Yeah, of course. Thanks.
Okay, thank Carlos. Tinley, please go ahead.
Thanks. So you mentioned that the bandpass changed from DR2. I wonder if the color-dependent extinction coefficient is a relation or the formula is provided somewhere in one of the papers?
No, we have not looked into that. So that's something that we don't do ourselves. So that will have to be done by the community afterwards. But yes, that will also change slightly with the change in the passbands. That's true.
Okay.
Okay, thank you. Genaro, go ahead, please.
Hi, Anthony. Thank you for this very useful talk. I'm thinking about the photometry. If do you expect that the photometry of future releases will be in a slightly different photometric system as from between DR2 and EDR3?
Yes, because so if you take the next release, DR4, that will be based on 5.5 years of data. And then we will have most of the data free of the problems we had in the beginning of the mission, where we had contamination, basically what we think is water ice being deposited on the mirrors and maybe even in the focal plane. And those, of course, change the optical characteristics and also the PSF. And that means the average instrument. And we cleaned up a couple of times, and now this is all gone. But if you then have a long period of very clean telescope compared to compared to a data release where most of the time the telescope was dirty, so to speak. These are very different instruments, in fact, and that's why the passbands change. So I do expect that still from DR3 to DR4 there will be changes. They won't be very large, but they will be there. And again from DR4 to DR5. So, and this, I think, is also the case, for example, in ground-based surveys. I'm pretty sure that if you look into the details of, let's say, the first Sloan data release compared to the more recent ones, and you're really interested in details of the passbands, that you will also find differences. It's just a reflection of the average instrument you're dealing with.
Thank you.
Okay, I don't see more raised hands, but okay, who is?
I have one. There's Antonio has a question.
Yeah, thank you. I didn't know how to raise my hand, sorry. Yeah, thanks for excellent talk, Anthony. Appreciate impressive result. I mean, before I make my question, was there possible to find the result that you had on the galactic center, proper motion and so forth, acceleration with DR2 at all, or that's only with EDR3?
No, that was only possible because the systematics in the astrometry were due. So we could have applied this. I mean, in fact, the reference frame paper for DR2 describes a vector spherical harmonic analysis, but they don't go into the acceleration simply because the systematics were too large. Yeah.
Okay, right, great. Now, my question is very simple. Somebody mentioned about the RUWE parameter. So up to now with DR2, what we have been doing is limiting, it to 1.4 or so, and then I made a histogram, and then you can see that really kind of has a nice Gaussian histograms around 0.6 to 1.4 centered on 1. Can you do this? Do you have to do the same to filter out, the parallaxes with EDR2?
Yes, you have to do the same. Investigate a bit for your sample what it looks like. But what you can do is you can look at this paper on the nearby stars, because the renormalized unit weight error by itself doesn't separate out the spurious astrometry so well anymore. But if you look in that paper, they show what features of the Gaia catalog you can use really to construct samples with clean astrometry.
Which paper was that again? Sorry.
It's the paper by Smart, is the first, well, Gaia collaboration, Smart et al., and it's about the Gaia catalog of nearby stars. So,
okay.
And it's already on Astronomy and Astrophysics website. It's an open free access paper at the moment, so you can download it. Yeah.
Thank you.
Okay.
So I think Luis also had problems finding his hand.
No, I found it. No.
Okay.
But I don't know if Luis wants to say some words.
Yes. Well, I agree with you, Anthony. The most outstanding slide, at least for me, is the last one. It's the first time I've seen a measurement of the acceleration due to the force field of the galaxy. This is very, very important, even if it's just one measurement. We model potentials because that's what we get from Poisson's equation. But what is responsible for the motion of stars is not the potential, it's the force field. You may say, well, the force field is just the gradient of the potential, but you could have two potential functions that do not differ from each other by more than 1%, and nevertheless the force fields, which are the gradient, are quite different, okay? So by providing this first measurement, you're putting the 0 point on the force field of the galaxy. And that deviation from the center of the galaxy gives you a little bit of measure of the asymmetry in the local mass distribution around the sun. So there's a lot of things that we can get from this. This is really very exciting news. Yep. The other thing, the value that comes out is very close to 10 to the minus 10 meters per square second, which is the characteristic acceleration that we supposedly MOND starts taking over. So we're getting very close to that border where we could start checking by direct measurement whether MOND is right or not. So I think that this is the promise of very exciting times in galactic dynamics in the future.
Yeah, and of course in the future releases, this measurement will become much more precise. So indeed, interesting things to look forward to. Yeah.
Looking very much forward to see it.
Okay, Francisco told me that. Okay, Antonio, who is Antonio? Go ahead, just wrote in the chat. Antonio?
No, I think he already asked the question just now.
I have another one, but I can wait.
But you can, of course, you're free to ask another one. Yeah.
Okay, there are no more questions. Okay.
Well, I do have one, if I may. Sorry.
Okay, go ahead.
I've been doing deep work with DR2, so I'm very interested in the changes and so forth. One crucial thing for us is since we are looking at dust distribution and so forth and polarization. So what about extinction estimates? Like AG or things like that, and correlation.
So those have not. No, they have not been updated. So we haven't redone those estimates. But in the next release coming out in 22 DR3, there will be new extinction estimates and also an extinction map. And these will be based not just on the broadband photometry, but taking into account the more information that's actually in the prism spectra. But yeah, that's for the next release.
Which will be next year, is that right?
Yes, in 22, the first half of 22.
Okay,
right, thank you.
No, this is Jesus. Go ahead, Jesus.
Hello, excellent talk. Well, I am wondering if we have a photometric transformation between DR2 and DR3. I ask this because we have a standard table that we use to estimate extinction, but these standard tables are based in DR2. So I don't know if it's possible to have some transformation between DR2 and DR3.
Yeah, we don't provide that simply because the systems are different, and when you start comparing them, you might run into things that are indicative of problems that were there in DR2 but no longer in EDR3. So we don't really want people to make comparisons because they're different. So yeah, as I just mentioned, the extinction business will have to be redone. We do provide transformations to other photometric systems for the EDR3 itself. So maybe that will help a little bit. But yeah, you will have to refigure out the extinction coefficients. But I don't think they will be dramatically different from what was done for DR2.
Oh, thanks.
Okay, thank you. Okay, if you want to say some words, turn on your mic and say some words. Perfect. Thank you, Anthony, for accepting the invitation. It was a nice, very, very, very nice talk. Thank you.
Great, my pleasure. All right.
Thanks a lot, Anthony.
Okay.
Thank you.
Bye.
Thank you. Nice talk. Thank you.
Thank you very much.
Rest, Anthony.
There's a nice glass of Flor de Caña waiting for me downstairs, so I'm going to enjoy that now. Yeah. All right.
Okay, bye.
Bye.
Thank you.
Thank you
Very much.
Thank you.